Good morning, my dear students. Myself, Captain Rail Sanju. Welcome to online classes from Department of Chemistry, Government Degree College, Peddapalli. In the last class, we covered introduction of heterocyclic compounds. We also discussed classification of heterocyclic compounds and various examples. Today we are going to discuss about synthesis of pheromone. In the last class, we also covered aromatic character and some of the preparation methods of pheromone. The next method of preparation, Hunt's pherole synthesis. In this method, reaction of alpha haloketones with beta keto esters and ammonia results in pherol. This is the starting material alpha haloketone on reaction with this beta keto ester in presence of ammonia will get substituted pherol. It is a single step reaction. From this reaction, what are the intermediate? How the involvement of reactants and intermediates? We don't know from this single step reaction. For this, we should observe the mechanism part of this particular reaction. In this Hunt's method, first of all, beta keto ester on reaction with ammonia. In this step, in the first step, it loses water molecule to form an intermediate, imine intermediate. From this intermediate, shifting of hydrogen here, migrating of hydrogen here, H plus ion shifted to this side. It converted as enamine, amine function group containing compound. It is called as enamine. This is the first step in the mechanism part. Now let us go to second step. That enamine, it formed in a first step intermediate. That enamine on reaction with the original actual reactant alpha haloketone in presence of acid, it gives this intermediate. From this, shifting of this hydrogen, loss of water molecule will get this intermediate. Here cyclization takes place and loss of halogen will get this type of intermediate. From this, here nitrogen positive charge is neutralized from rearrangement of pi electrons. Finally, we'll get substituted pherole. This is the final mechanism part of Hunt's synthesis. Now let us go to chemical properties of pherole. This chemical properties, some of the reaction part is also involved. Pherole is aromatic and more reactive than benzene. When we compare with benzene, benzene is a purely carbocyclic and it is a beautiful example for aromatic compound. It is a more stable compound. But compare with this benzene, pherole undergoes reactions. It gives electrophilic substitution reactions such as halogenation, sulfonation, nitration, etc. In all these reactions, electrophile attacks on cyclic ring. Why this electrophile attacks on cyclic ring? In the last class we have already discussed, due to the delocalization of electrons, the cyclic ring gets negative charge, more electron density on the cyclic ring. Due to that reason, electrophile positive charged species easily attacks on cyclic ring. It also undergoes diazotization and Remote-Tymon reactions, while benzene does not. Pherole is more active, reactive compound because undergoes this type of special reactions. Now let us go to discuss about acidity character of pherole. I would like to explain clearly about weak acidic character of pherole. In pherole, all the carbon atoms and nitrogen undergoes sp2 hybridization. This sp2 orbital of nitrogen and 1s orbital of hydrogen overlap to give NH bond. In this case, we can compare this pherole molecule NH bond and this heteroatom bonds with the alkyls, because that it seems to be secondary amine R2NH. But Pyrrole does not show basic character. Pyrrole does not show basic character. In this case, breakage of this NH bond, it loses proton. It gives proton because that pyrrole is a weak acid. The pK value is 7.5. Here the formation of pyrrolyl anion is a strong base. Pyrrolyl anion is a strong base. The acidic character of pyrrole we can also explain with other reaction. Pyrrole on reaction with strong solutions like potassium hydroxide base, it forms salts and water. Based on this reaction, the pyrrole exhibits weak acidic character. Weak acidic character because that it undergoes reactions with a strong base. Is it clear, all of you? Is it clear? Basicity of pyrrole. Here, a pyrrole are a purely aromatic compound. On reaction with the H plus ion, it gives non-aromatic cation. Non-aromatic cation. It is an unstable compound, but in the earlier reaction, it gives pyrrolyl anion. It's a stable compound. Pyrrole is a weak base. Protonation breaks aromaticity. Lone pair participates in conjugation and thus it is not readily available. This is about basicity character of pyrrole. Now let us go to very interesting topic, electrophilic substitution reactions. Pyrrole undergoes electrophilic substitution reactions at second position. Pyrrole generally reaction with electrophile. It is a possibility to attack electrophile on C2 position and C3 position. When the electrophile attacks on C2 position, it gives more number of resonance or contributing resonance structures. When the attack of electrophile on C3 position, it gives less number of resonance structures. Here please observe in what way. Please observe this reaction. Pyrrole on reaction with the electrophile positive species, generally positive species attacks on cyclic ring. If electrophile attacks on second position means this pi bond breakage takes place, that pi bonded electrons shifted to C2. C2 carbon gets negative, easily attacks electrophile. In that case, C3 carbon gets positive. This is one of the resonance structure. From this, we can write another. If this pi bond electron shifted to in between C3 and C4, it forms a new pi bond and C5 carbon gets positive. This is another resonance structure. From this, the lone pair electron of heteroatom if donates to cyclic ring to form a new pi bond in between heteroatom and C5 carbon. C5 carbon. This is the another resonance structure from attack of electrophile on C2 position. From this we cannot write another one. Here loss of electrophile we will get a first compound. When electrophile attacks on C3 position, other side we will observe. If the pi bond electron shifted to C3, C3 gets negative attack of electrophile on that place. This one. From this, pair of electron donates to cyclic ring. Heteroatom gets positive. New pi bond is generated. From this, we cannot produce another structure based on these two reactions, these two contributing structures. We understood that attack of electrophile on C2 position, it gives stable structures. Here, please observe the reasons, two reasons. C2 attack gives more resonance contributing structures than C3. Extra stable contributing structure generates upon C2 attack. C2 attack. Due to all these reasons, generally electrophile attacks on C2 position will get C2 substituted product for this pheromone. Now let us go to another evidence for the formation of more amount of C2 product. What is the reason here? Another type of with use of energy diagram we can explain easily. Here energy level and time with the time. Here we are representing thick line energy level is belongs to attack of electrophile on C2 position intermediate. It is a lower energy when compared with the attack of electrophile on C3 position. C3 position is a higher energy level compare with C2. This higher energy level we are representing with the dotted line. Dotted line. This is a perfect evidence to produce more yield of C2 product. Energy diagram shows C2 attack forms more stable intermediate than C3 because it is a lower level. It is a excited state is a lower level compared with the C3 intermediate. Hence, C2 preferred over C3. C2 products are more yield from C2. Is it clear, all of you? This is the another evidence for formation of C2 product. Now let us go to various different reactions of electrophilic substitution of pherole. Here first on reaction with the hydrogen. Pherole. Here pair of electron donates to cyclic ring. This C3 carbon gets negative, and that negative charged carbon abstract H plus ion will get 3H pherolium ion. It's a positive charged species, positive charge on heteroatom because it is named as pherolium ion. If the electron pair donates to left side in the cyclic ring, here 5 bonded electrons shifted to this side, and these 5 bonded electrons increases electron density on C2 carbon. H plus ion attacks on C2 carbon. It gives 2H pherolium ion. 2H pherolium ion. These two compounds are positive charged species. Is it clear, all of you? Now let us go to actual electrophilic substitution reactions, various reactions. First we will discuss nitration reaction. Pherole on reaction with the nitric acid in presence of acetic acid. Instead of this acetic acid, we can also use AC2O, acetic anhydride. Acetic anhydride. In this reaction, generally produces nitro group electrophile. That nitro group electrophile attacks on C2 position. It forms 2 nitro second position, second substituted compound, 2 nitro 1H pherole. This is about nitration. Next, sulfonation. Pherole on reaction with the sulfur trioxide in presence of pyridine to forms second substituted compound pherole to sulfonic acid. Is it clear? second substituted compound. Now let us go to halogenation reaction. Halogenation reaction, pherole on reaction with this chlorine molecule. Here also Cl plus electrophile attacks on second position, will get 2-chloropherol. 2-chloropherol. Is it clear? Now let us go to another reaction. Here a reaction with the acetic anhydride. It is also represented with the Ac2O, acetic anhydride, in presence of boron trifluoride. Boron trifluoride. This reaction will get 2 on second position, second substituted pherole, 2-acetyl pherole, 2-acetyl pherole. These are the various examples of electrophilic substitution reactions. In the same pherole on reaction with the iodine I2 molecule, in presence of strong base, when we use sodium hydroxide, strong base, in this reaction it gives a different compound, that is tetraiodophirol. Tetraiodophirol. In this reaction it will get a different compound. The next reaction is reduction reaction. Pherole on reaction with the zinc in presence of acetic acid at room temperature to forms 2,5-dihydropherol. Second and fifth position gets reduced. Is it clear? This is the structure. Second and fifth position gets reduced. Will get this type of product. But in presence of strong reducing agent like platinum, it from this reaction after reduction it gives pyrrolidine. Pyrrolidine, it is a purely saturated compound, completely reduced compound. Is it clear, all of you? Is there any doubt in this reduction reaction? Now let us go to the special reactions like Riemer-Tiemann reaction. Riemer-Tiemann reaction. In this reaction, pherole on reaction with the chloroform in presence of potassium hydroxide. This chloroform CaCl3 trichloromethane, it is also called as trichloromethane. Trichloromethane on reaction with the potassium hydroxide, from this first we will get dichlorocarbene intermediate. This chloroform CaCl3 does not involve directly. That chloroform converted as active intermediate. Active intermediate, that is called as dichlorocarbene. Dichlorocarbene is a intermediate. It is very highly react to. Pherole on reaction with the dichlorocarbene. Carbene will get intermediate on hydrolysis. On hydrolysis, it forms 1H pherole 2-carbaldehyde. It is also second substituted compound. On second position, it is a aldehyde functional group. It is called as 2-carbaldehyde. The same reaction, dichlorocarbene attacks on second position. The same reaction will proceed in another way, cyclization. In another way, here cyclization takes place. This 5-membered ring is converted as 6-membered ring. Here loss of HCl, loss of H and Cl. From this reaction, it gives 6-membered ring. Please remember this special reaction. It's kind of well noted reaction. It's a name reaction. Please remember. 3-chloropyridine. Third place, chloropyridine. Pyridine is a 6-membered ring. Just now we learn about 5-membered rings only. All these pherole, furon, thiophene, all these 5-membered rings we are discussing. It is a 6-membered ring. From 5-membered ring, we can produce 6-membered ring based on this Riemann-Tiemann reaction. Okay, is it clear? Now let us go to another reaction with the Grignard reagent. Reaction with the Grignard reagent. Here pherole on reaction with the Grignard reagent, methyl magnesium bromide. It is actually, its general formula is RMGX. R means alkyl methyl, Mg magnesium, X halogen bromide, RMGX. It is a general formula of a Grignard reagent. Here we are using methyl magnesium bromide. On this particular reagent, we'll get this intermediate, second substituted intermediate on second pherole on second position, substituted magnesium bromide. This is the intermediate. This intermediate on reaction with further alkyl bromide and another side carbon dioxide in presence of hydronium ion. In the first case we will discuss this second substituted pherole on reaction with the alkyl bromide. In the first case it produces 2-ethyl 1H pherole. In the second case, here please observe second substituted intermediate on reaction with the carbon dioxide in presence of hydronium ion, H3O plus, H2O plus H plus ion, H2O. hydronium ion. From this reaction we'll get this product 1H pherole 2 carboxylic acid on second position. On second position, this oic acid, carboxylic acid functional group is bonded on, is attacked on second position. We'll get this type of product. Is it clear, all of you? Grignard reagent on reaction with the Grignard reagent. Now let us go to applications of pherole. Applications of pherole. Pherole is essential to the production of many different chemicals. In the chemical industry, pharmaceutical industry, it is a useful compound, pherole. N-methyl pherole is a precursor to N-methyl pherole carboxylic acid. It is a building block in pharmaceutical chemistry. It's a fundamental compound, pherole. It's a building block in pharmaceutical chemistry. Although there is a claim that pherole is used as an additive to cigarettes, it is typically listed as a constituent of tobacco smoke and not as an ingredient. Pherole is also used in commercial and pharmaceuticals. Pherole subunit has diverse applications in therapeutically active compound including fungicides, antibiotics, anti-inflammatory drugs, cholesterol reducing drugs, anti-tumor agents, and many more. For example, pyrocyclidine. It's a pyrrolidine ring containing compound pyrocyclidine. Pyrocyclidine is used in the treatment of Parkinson's disease. These are the major applications of pherole. Is it clear, all of you? Pherole is the one of the suitable example for 5-membered ring. Today we completed this example. Today we are going to discuss about just introduction. Tomorrow we will continue this topic. Just introduction we will discuss today. Furon. Furon, it is also one of the example of 5-membered ring. 5-membered heterocyclic compound. In this heterocyclic compound, the heteroatom is oxygen atom. Here, oxygen atom. The remaining 4 carbons are present in the cyclic ring. In this cyclic ring, it has 2 pi bonds. Here also same, the lone pair of electron on oxygen atom, that is heteroatom, is involving in the formation of cyclic delocalization cloud. Here please observe the clear structure with the orbitals. All the 4 corners are carbon atoms, 4 corners. Here heteroatom, all these 5 atoms, 4 carbon atoms and 1 heteroatom, are in the same plane, Here on oxygen atom there is a sp2 hybridized orbital, and another one unhybridized p orbital is also present. In this unhybridized p orbital, it carries a lone pair electron. Okay, is it clear? Lone pair electron. Now we will go to discuss about aromaticity of this particular furon. Aromaticity of furon. In the structure, we have already observed clear atoms arrangement and orbital structure arrangement, even though we are discussing clearly. In the furon have 4 carbon atoms at 4 corners and 1 oxygen atom. All these 4 carbon atoms and 1 oxygen atom undergoes sp2 hybridization. After formation of this sp2 hybridization, new hybridized orbitals, all these 4 carbons and 1 oxygen is in same plane. It makes a planar furon ring structure. In this ring, each ring atom, each corner of atom also contains unhybridized p orbital. That is, that unhybridized p orbital is perpendicular to the plane of sigma bonds. Please observe in the structure. These 5 atoms in the same plane, but unhybridized p orbitals, all these lobes, this is the plane, but all these lobes, unhybridized p orbitals, are perpendicular to the plane of this sigma bond. plane of this sigma bond. Here p orbitals are parallel to each other. What are those? 4 carbon atoms, p orbitals, unhybridized p orbitals, and one heteroatom. All those p orbitals are parallel to each other. So overlapping between p orbitals is possible. 5 orbitals are participating. P orbitals are participating in this overlapping to form a cyclic delocalized electron cloud. In the last class, Pheromone, we have already discussed to formation of this electron cloud. It is called as aromatic sextet. But here please remember the important information is in this electron cloud formation 5 p orbitals, that means 5 atoms, are involving in the cyclic ring formation, electron cloud formation, but the total number of non-bonding electrons are 6. This information, please remember, it is very interesting in this electron cloud formation. The total number of non-bonding electrons are 6. How is it? Means 4 electrons from 4 carbons, but 2 electrons, the pair of electron from one of the oxygen, is involving. Total 6 electrons are involving in the formation of cyclic electron cloud. Once again I am telling, 5 p orbitals are participating in this overlapping to form a cyclic delocalized electron cloud is called as aromatic sextet. Due to this reason, the resonance of 6 electrons, it follows the Huckel rule. It follows the Huckel rule. So the furon, it is same related with the Pheromone. Instead of heteroatom nitrogen, here we are using oxygen atom, furon. So this furon is aromatic. This is a very stable compound. Once again, please observe in the structure. Here 4 corners, 4 carbon atoms, 4 carbon atoms and one of the heteroatom oxygen. 5 atoms. These are all this sigma bond represented 5-membered ring. It is a purely sigma bond. All these sigma bonded 5 atoms in the same plane, but on the corners of each carbon and heteroatom unhybridized p orbitals. On the carbon atom, unhybridized p orbital carries a single electron, alone electron. Here also alone, alone, alone. All the carbons. Alone electron, 4 carbons, 4 electrons. Here on the heteroatom, unhybridized p orbital carries a pair of electron, 2 electrons from heteroatom, that is oxygen. These 2 electrons and 4 electrons are participating in this p orbital, unhybridized p orbital partial overlapping process. Partial overlapping. Here the five atoms in the same plane, the above the plane there is a electron cloud above the plane, one ring, and another below the plane. These orbitals to form a cyclic delocalized electron cloud above the plane and below the plane to form a circular to form a circular electron cloud. Is it clear? Is it clear, all of you? This is about aromaticity, Furon aromatic character. Now let us go to synthesis of furon. Synthesis of furon. This is the first method of preparation. First method of preparation, Paul-Knorr synthesis of furon. This is very important reaction. This is the name reaction. It is very important in further studies also. Please remember, once again I am telling, it is very important in further studies and in the any entrance examinations. They may be asked questions from this reaction. Please remember. Okay. Paul-Knorr synthesis of furon. Acidic catalyzed cyclizing dehydration of 1,4-dicarbonyl compounds. Here also cyclization takes place. Cyclization of 1,4. If it is the first carbonyl, it may be 1 and 2, 3, 4th carbonyl. 1,4-dicarbonyl compound in presence of acid. From this loss of 2 moles of water molecule. Loss of 2H2O, 2 moles of water molecule, will get furon. But here in this structure, please observe, on second position and fifth position, we are representing a alkyl group. here alkyl methyl. Okay, methyl. It is a substituted. It is not a normal furon. It is a substituted furon. Substituted furon we are getting. Is it clear, all of you? Earlier, this is the single step reaction. From this mechanism we can understand clearly. The starting material, it is a 1,4-dicarbonyl compound. 1,4-dicarbonyl compound in presence of acid. One of the carbonyl oxygen protonated. Here, next, loss of proton. Here, loss of proton and cyclized. Here, OH hydroxy group. Hydroxy. From this, what happened? In presence of acid, this intermediate is formed. From this, loss of H plus and H2O. Loss of H plus and H2O. Finally, we'll get a substituted furon. Where is that substituents? Second position, methyl. This line indicates methyl. Here methyl, and fifth position, another line. This indicates another methyl. 2,5 dimethyl furon. 2,5 dimethyl furon. This is the final product from the Pyrrole synthesis. This Pyrrole synthesis in a single step reaction. From the mechanism part we understood clearly. Is it clear, all of you? Another type of synthesis from carbohydrate. From carbohydrate we can get furon compound. Here, two steps involved in this synthesis, in this method. In the first step, distillation of carbohydrate with sulfuric acid. Distillation process. We'll get a step 2, catalytic decomposition of furfural in steam. Here please observe pentose. It is a carbohydrate in presence of acid, H plus ion. We'll get furfural in presence of acid, H plus ion. Pentose is a sugar. Pentose sugar in presence of acid, sulfuric acid, or we can use any strong acid. We'll get the intermediate is furfural. It is a substituted furon. On second position there is a aldehyde functional group. On second position in the furon aldehyde functional group, it is named as furfural. This furfural intermediate catalytic decomposition in steel in presence of calcium oxide. In presence of calcium oxide, it forms furon. Finally, we'll get, after removing of this second substituted aldehydic functional group, finally we'll get a normal furon. Furon. Is it clear, all of you? Now, this is about synthesis of furon. Today, I think it's enough. Tomorrow, we'll discuss the various reactions, the reaction part, various reactions of this furon. And furon undergoes electrophilic substitution reactions. Those reactions, which one is more stable, which is less stable, we'll discuss tomorrow. In this today's class, all these important name reactions, please remember and please write 2-3 times. Please practice it. All the students, please practice each and every name reaction. These are all the name reactions are very important in future studies and in the mainly in the entrance examinations. Okay, students, in today's class, is there any doubt, all of you? Is there any doubt? Okay, we will meet tomorrow in the same time. Okay, right.